Welcome to MHF4U, Grade 12 Functions, Section 3.1. Today we'll be exploring polynomial functions. So first of all, let's start with this chart we have here of polynomial expressions, of a list of polynomial expressions and ones that are not polynomial expressions. So let's just look through and see what differences we can find between these two. Right away, we can see that everything that is a polynomial expression has a variable attached to it with a degree, and that each degree that is attached to it has a integer value. There is no, x's to the power of half. There's nothing like that. You only have x's to the power of whole numbers. Therefore, they're only to the power of integers. Compare that here with things that are not polynomial expressions, and you see here that this is x to the power of a half. The next thing we can see here is that there's no rational functions, right? So for example, this would be a rational function where the x is in the denominator. We don't have that on the left side where we have polynomial expressions. We also see that there's a leading coefficient for every single polynomial expression given here, and that there is always a highest degree for each polynomial expression. So these are some characteristics we find when we compare polynomial expressions and things that are not polynomial expressions. Okay, so now that we have some ideas about what might make something a polynomial expression and what might not make it, let's look at some more formal definitions. So a polynomial function formally is a function of the form f of x is equal to an times x to the power of n times a to the subscript n minus 1 times x to n minus 1, etc., etc., to the point where you get to a to 0. So this might look complicated, but all we're saying here is that the degree of the function decreases as each successive term is added. So for example, we could also have a function, polynomial function, that could be like 5x to the power of 5, then 5x to the power of 4, then 3x to the power of 3, 3x to the power of 3, and this would keep decreasing until we get to x, and then we get to just a constant at the end, which could be, say, 6 at the end. So this is how we define polynomial functions, where each number is a real number, n is always a whole number, as we mentioned previously, and that the equation will be defined in a polynomial expression, as we see here. Okay, so now that we have that, let's look at a summary in more detail. So again, we have the definition here, and we also have multiple examples which I want to look at. So we can have, say, a linear function, that would be polynomial. We can have a quadratic, that could be polynomial. We can have a quartic function to the power of 4. This would also count as polynomial. Now, the other thing we need to know is that any polynomial expression, the exponents in the variable must be whole numbers, as we said before. A polynomial function is any function that contains a polynomial expression in one variable. So the degree of the function is the highest exponent in this expression. So for example, here, this expression has a degree of 3. If we look at the other examples, this expression has a degree of 1. This has a degree of 2. This has a degree of 4. Etc., etc. So the nth finite differences of a polynomial function, degree n, are constant. Okay, the domain is a set of real numbers for every polynomial function. The range is maybe all real numbers, or it may have a lower or upper bound, but not both. The graphs do not have horizontal or vertical asymptotes for polynomial functions. So for example, what we saw here, this was a rational function, right? And with the rational function, we have horizontal asymptotes, horizontal or vertical asymptotes. So with polynomial functions, we do not have that. The graphs of polynomial functions of degree 0 are horizontal lines. So for example, if we had, let's say x is equal to 1, that would be of degree 0, so that would be a horizontal line, for example. The shape The graphs of polynomial functions of degree 0 have horizontal lines. The shape of other graphs depend on the degree of the function. So for example, here are some five typical shapes for functions of various degrees. So linear we're very familiar with, n is equal to 1, we know that. Quadratic, n is equal to 2, we're familiar with that as well. Cubic, n is equal to 3, so this might be new to you, but in general you'll have this shape for a cubic. Quartic, n is equal to 4, and quintic, n is equal to 5. Now, something that you might be seeing is, well, as you move through, you see that, well, look, the number of turning points appears to be the degree minus 1, which is true, right? So here we have n is equal to 2, and the turning point is 1. Here, n is equal to 3, we have 2 turning points. N is equal to 4 here, we have 3 turning points. N is equal to 5, we have 4 turning points. And that is one way that you can use to distinguish between functions, and also when you draw your functions. That's something you can use. So here we can look in more detail then. Determine which graphs represent polynomial functions. Explain how you know. Alright, so here we have our list. So polynomial A, D, and E, not polynomial B, C, and F. So let's look at why. So first of all, we can see here that for A, this is likely a quartic function because we have three turning points, so it's probably degree 4. We can also see that it's downward facing, and that it has a negative leading coefficient. So yes, it's polynomial. For C, this appears, this isn't a polynomial function. We don't see any turning points here besides the 1, but it doesn't really follow any shape of the polynomial functions we're familiar with. Same with E, this is a polynomial function. B, this is not a polynomial function. D, this is a polynomial function, this is a quadratic function. And F, this is not polynomial, this is a sine function. Alright. 2. Determine whether each function is a polynomial function or another type of function. Justify your decision. Okay, so here for part A, we can see that the degree of the entire function is 3, and that every single exponent we have here is a whole number. So that's how we know it's polynomial. So in this case, it would be a 3rd degree, so it would be a cubic function. For B, we know it's polynomial again for the same reasons, whole number coefficients only, and this is a quadratic function. For C, we know it's polynomial, it's actually linear, again, whole number exponent. And for F, we know it's polynomial because, again, this is a whole number exponent. So actually for this, we would need to expand it out beforehand. So we would have to f of x is equal to x times x squared minus 2x plus 1. So it becomes x cubed minus 2x squared plus x. So then we know that this is degree 3. Okay. So then, the ones that are not polynomial, D and E. So for D, we can tell that this entire function is to the power of 1 over 2, right? And, 1 over 2 is not a whole number, so we know it's not polynomial, it's something else. In this case, it's a square root function. And for E, we can tell that, again, we have the x in the denominator. This is clearly a rational function, and it's not polynomial. Okay. So now we can move into so now question 5. Draw a graph of a polynomial function that satisfies the following characteristics. So f at negative 3 is 16, f at 3 is 0, f at negative 1 is 0. That's our first step. We're going to draw out. So I've identified here all the points they've given us. Perfect. The next thing we're going to do is write the y-intercept, which is 2. We have that as well. Then we're going to look at the restrictions. So f at x is greater than or equal to 0 when x is less than 3, and f at x is less than or equal to 0 when x is 3. So that's what tells us the shape of the function here, beyond these points. And that's how we know, okay, which way, especially in this area right here, right? Because everything else you can kind of follow the points that are given to you, but right here you need to know what the behavior is. So that's how you can use the restrictions they give you to then draw the function. And they also tell you its domain is on the set of real numbers, so you know it's continuous throughout, and that the function will continue on infinitely. This way and this way. Perfect. Okay. So that's all for our introduction to polynomial functions. Be sure to understand this definition well and understand the basic polynomial functions you can have, and also how they can be transformed when you can determine algebraically or graphically when a function is not polynomial or is polynomial. And with that, thanks for watching. I hope you enjoyed this video, and if you have any questions, as always, please contact us on passionateminds.com. Thank you.